Hello everybody, thank you for joining this webinar today. My name is Leisha Mummin and I am the chair of the IMechE Birmingham Young Members Panel, and we are the ones that have organised this session today. Just some quick housekeeping before I introduce the session. We will be having a Q&A at the end of the talk, which will be in the last 15 to 20 minutes. You can post your questions during the webinar, and there should be a box on the top right-hand side of your screen, and then we can ask the questions at the end. So the webinar today is on the HydroFLEX project. This is a partnership between Porterbrook and the Birmingham Centre for Railway Research and Education. And this is the aim for having the UK's first hydrogen train and how that can be rolled out to the rest of the UK's network. So unfortunately today our speaker was going to be Stuart Hillmansen, and he is part of the research centre at the Birmingham University. Unfortunately, he has to be present on site today, so will not be leading the session. But we have Kevin Blacktop who will be taking the session today, and he's head of the project delivery for the project and does a lot of the mainline testing for this project. Now, Kevin is also the chair of the Worcestershire panel in the Midlands region. So he has great engagement with the IMechE and also runs events like we do. So I'll just hand over to Kevin and then I'll be back for the Q&A at the end. Kevin?
Yeah. Good afternoon, everybody. Thank you, Leisha. So I'm Kevin Blacktop. I have been working at the University of Birmingham for just 2 years, which neatly overlaps with the HydroFLEX project. Before that, I used to work at Network Rail and looked after the strategic university partnerships. So I've been involved with R&D for the last decade, really. So I'd like to talk to you today about HydroFLEX, the UK's first hydrogen-powered train. And so we'll make a start. So why fuel cells? So the Birmingham Centre for Rail Research and Education has had a long interest with the application of fuel cells for rail vehicles. We are particularly keen to expand our work on decarbonisation. We've been involved with air quality research projects. We did some work on Birmingham New Street Station, and we've basically started to look at the opportunities really for the rail industry to decarbonise. It's quite a challenging industry for that reason, partially because of the lifespan of trains. They often have service lives of sort of 25 to 35 years. So if you think in terms of road vehicles, the shorter lifespan of those means things like low emissions equipment improvements that are made on road vehicle fleets get updated on a more regular basis. So the opportunity for rail fleets are much more complex. Vehicle life is longer. There's the complexities about how the industry works, how it's funded, how train fleets are owned by Roscoes, which are the companies that own the fleets. The operators, passenger train operators, they lease the fleets according to what routes that their franchise allows them to use. So making decarbonisation improvements is more complex for the rail industry, but nonetheless, there is a growing realisation that the rail industry needs to embrace decarbonisation and move forward. So this is where we want to discuss today. Yes, sorry, I just missed the button to go to the next page. So Birmingham Centre for Rail Research and Education has been writing papers and been involved in key research since 2003. We've been part of the International Hydrail Conference since that time, hosted that conference at least twice. There's been a growing interest in this type of technology, and there is already a hydrogen fuel cell train in operation in Germany, first one in Europe, the Alstom IMechE train. So we have basically been building up the information and the background knowledge to be able to adopt this technology and see how we could implement it onto the UK rail network. We started off at a very small scale, and this is our small scale. This was the first hydrogen train to run in the UK. It was actually developed for the IMechE Railway Challenge, and it's competed on a number of occasions. In its original form, it looked more like a photocopier on wheels, which is on the left, and it's been steadily improved and adapted, and it enabled us to understand the basics about control systems and the beginnings of the sort of safety requirements. And it was a good educational tool, not only for the students that were involved with the IMechE Railway Challenge, which, by the way, is a fantastic event, no matter what type of locomotive you put into that competition. It's also was enough to start sparking the interest in the wider rail industry. So the Railway Challenge, if you've not had any experience of it, it enables teams from various universities and commercial organisations, industry organisations, to build a small gauge locomotive that competes in a number of challenges to achieve an overall winner. That includes its pulling performance, braking, ride comfort, noise. I think there's probably about a dozen categories now that these trains are put through. So a fantastic event, and if you're in the rail industry and you're looking for something to challenge your students and graduates and apprentices, I would heartily recommend that. There's nothing like building from scratch a vehicle and then testing it to get that learning experience and also the teamwork experience. So that's my plug for the Railway Challenge done. So a fuel cell. A fuel cell is a device that takes hydrogen and combines it with oxygen from the air, and it generates electricity. It's an electrochemical reaction. There is no combustion, but you do get waste heat. It's very quiet, and over the years, fuel cell technology has improved so that in terms of lifespans, they're getting better and better and can now challenge diesel engines. And the fuel can be generated from multiple sources, so it is possible to do a zero carbon generation. And at the moment, fuel cells are running about 50% efficient, so 50% is released as heat. So the fuel cells require a cooling system, but in terms of where they are compared to internal combustion engines, diesel engines are probably in the sort of early 40% now, maybe a little bit higher. But so there's still an advantage for fuel cells over internal combustion engines. So what does it look like? It's a bit of a black box, really. So the picture, I don't know if you can see my cursor, but the picture on the bottom shows the fuel cell. And underneath here is a compressor and a cooling system pump. And over on this side here, you can see the radiators for the cooling system. The cooling system runs about 60 degrees C, so you have a slightly larger radiator than you would for an internal combustion engine because of the delta between the ambient air and the cooling system input. But within the fuel cell itself, the hydrogen is fed in at a very low pressure, probably 1 or 2 bar, and it enters via an anode, which strips the electrons from the hydrogen. The positively charged protons then pass through a membrane to the cathode, and the negative electrons are forced through an electric circuit, which generates the electricity. And then after that, the electrons and protons get recombined on the anode side, and they also are combined with the oxygen or the air from the oxygen from the air to produce the byproduct, which in this case is water and heat. So this fuel cell is about 100 kilowatts, and they're available in a variety of sizes at the moment. The larger ones that are commercially available are probably around about the sort of 300 kilowatt size. They can be made modulus to build up the power banks. There's actually a submarine in service with the German Navy that has considerably more power. So I think that there's lots of opportunity to upscale these in time to come. So we have competition for hydrogen. So diesel's got some significant advantages. Diesel engines are much cheaper to buy than fuel cells. They're made in much larger volumes and in a variety of applications. They're very much a well-known, proven technology for our applications, and it's easy to get fuel. It's available everywhere. Diesel is far more energy dense than hydrogen. It's approximately, well, because it's a liquid, first of all, it obviously is a lot more dense, so you can get about 10 times the same amount of energy out of a diesel tank size for size. OLE is also a competition for hydrogen, and that is probably the best option in terms of decarbonising for the future. It's quite efficient, about 80% efficient, and the only real downside to it is the fact that the costs of implementing extensive OLE networks, overhead power line networks, is very high. As well as you also need to buy the modified rolling stock to suit it if you're going to electrify from scratch. So at the moment, electrification for the UK network's circa 50%, 55% maybe. So there's quite a bit of opportunity to look at alternative power sources, as well as allow for additional electrification in the future. So what's the drivers for hydrogen? Air quality and climate change is, of course, of concern to everybody. We can't ignore the fact now of mankind's footprint, shall we say, on the planet. So we need to consider also that the UK is changing its generation mix for how it produces electricity. We're seeing much more renewables, probably far more renewables than perhaps was first anticipated. The rollout of that has been much higher than first thought. There's also considerations for fuel security. OLE expense is listed here, and I think that needs a little bit more explanation. So overhead power line systems are very good for intensive high-speed use. If you're going to run a train all day, every day at 125 miles an hour, there's nothing to beat having overhead power lines. The problem comes on more rural routes, or the sort of feeder routes for the major routes, where the intensity of the service isn't so high, and you have the cost of possibly going on more twisty or routes with elevations that make putting OLE much more expensive. So the business case for OLE in some routes would not be very good. And so what is the alternative to diesel? So this is why we've started to look at hydrogen. So when we first talk about hydrogen, everybody says, yes, it's very dangerous. And it is, in so much as it's explosive from about 4% mix into air. So it does have, it is very flammable gas. And also we need to store it at quite high pressures, to be able to put get the gas in storage in the quantity that we need. So for rail applications, we're probably looking at 350 bar pressure in the tanks. For road applications, for cars, you're probably looking at 700 bar. So that is a significant challenge. However, there are processes and standards in place that have regulated how these storage systems work. But unlike diesel, if there's a leak, the gas is much lighter than air. It disperses very, very quickly. Fuel cell themselves, oops, not quite sure what happened there. The fuel itself is fed into the fuel cell at very low pressures, so it does get reduced from the tank system. We supply from the tanks at 350 bar to the fuel cell at around about 8 bar, and then into the working sort of membrane area at around about 1 or 2 bar. The rail industry has taken some comfort about using hydrogen by the fact that there's been some road applications and there's some standards that have been built for transportation, notably EC 79, that has dictated how these systems should work. So whilst it needs care with handling, the processes and procedures and requirements for the systems are now well known. So it should, if the railway adopts these standards going forwards, they're proven, and we feel like it is a good way forwards. And the rail industry has actually got form of using high pressure vessels, because if you think of steam engines in the past, which were at the very front of the train, they were certainly running at high pressures, and steam expands about 1,000 to 1. So it's something that the rail industry is used to, even though first of all it would have initially thought it wasn't. It was something that's new and novel. So we do need a fair amount of hydrogen. So we've calculated, looking at various modelled duty cycles, that we would want about 65 kilograms per day for a vehicle running a 500-mile range at about 75 miles an hour. So you need many tons for a whole fleet of diesel engines, for trains, sorry. And there's different ways of doing this. We can strip out and reform the hydrogen from natural gas. We can use electricity from a grid, or we can locally do this. Now, with the decarbonisation mix and the energy mix that's going on in the UK, the opportunities for doing more localised creation of hydrogen in a sustainable manner will be likely the way forwards. And if that happens, we're likely to start to see the fuel cost drop lower than diesel in the future. So our storage systems, I've mentioned before the pressures. So in our HydroFLEX train, we have been running the tanks at 350 bar. When you double the pressure, you don't get double the amount of hydrogen. It's only about 60% more, and you use more energy in compressing the gas. Also, the tanks need to be a lot stronger. There is opportunities to store it as a liquid, but to do so takes a lot of energy, and that's really the sort of application that you're most likely to see in aerospace. So a good example of a liquid storage of hydrogen would be the space shuttle main engines, the big fuel tank. So not really the sort of thing we'd want on a train. So what is HydroFLEX? HydroFLEX, its name is based on hydrogen for the hydro part, of course, and Flex is part of Porterbrook's sort of innovation fleet of trains. So Porterbrook is a partner with BCRRE. We launched that partnership in September 2018 at InnoTrans, the big international rail show held in Berlin. At that point, we hadn't done any pre-work. This was an opportunity to work with Porterbrook, who are a fleet owner, a major fleet owner, a Roscoe, and they offered us the opportunity to take one of their existing Class 319 trains and turn it into a hydrogen technology demonstrator. We've done this. We've put all of the equipment inside one of the coaches as opposed to underneath it. It was deliberately not done as a production intent type of vehicle. We wanted it to demonstrate that hydrogen was feasible, that the standards and approaches that we could take would find approval from the rail industry. We launched the vehicle at Rail Live in June 2019. That was just 9 months after we signed the original deal with Porterbrook Innotrans, which from a standing start was a fantastic achievement. We managed to take passengers on a short run round the Rail Live event test track, which was at Long Marston in Warwickshire. And we've got a lot of positive publicity, including BBC Breakfast Show did a broadcast live, and we were able to demonstrate the technology to a much wider audience than just the industry event. So, what is HydroFLEX? So, it's the UK's first full-sized hydrogen train. As I say, it's based on a Class 319. So, this is a 4-car train. It has a power car. It has the ability to use overhead power lines and also third rail DC shoe collector equipment. We have put the hydrogen fuel system and battery system into that power car coach. Then you have a trailer car and 2 driving cars, so it's a 4-car train. And this is what the power car looks like in the centre. So we have a control system on the left. We then have the hydrogen storage tanks in the middle, the hydrogen fuel cell, and the traction battery on the right-hand side. Now, I don't know if you can see my cursor, but if you see where it says hydrogen fuel cell, you can see the fuel cell and the cooling system are there, and underneath are the pumps and the compressor for the air. The hydrogen tank, we've got 4 tanks that carry 20 kilograms of hydrogen. The control system allows us to control the train using, we can power the train using just the batteries. We can power the train just using the hydrogen. We can use the hydrogen to charge up the batteries, and we can also run the train using the batteries and the hydrogen combined. So it's quite a flexible control system, and it gives us the ability to maximise the flexibility of how we can use the train, how we can extend the range, how we can get the maximum performance. So the tanks are carbon fibre, run at 350 bar, 20 kilograms of hydrogen, which allows us to run the fuel cell for about 4 hours. EC79 is the standard for the hydrogen systems, and it's very much about putting in the right safety requirements. So there's things like flow regulators, shut-off valves, fire protection. These are very important to make sure that we handle this fuel correctly and consistently correctly. It also includes detection systems, and in that respect, once you've got these systems in place and it's maintained and designed, installed and maintained correctly, the system is robust, and we have high confidence. The fuel cell, we've got a 100 kilowatt fuel cell. It takes in hydrogen about 8 bar, but it does reduce that further when it actually puts the hydrogen into the inner parts of the fuel cell. We control the outputs of the fuel cell using our control system, and the balance of the plant is what I was mentioning earlier, that we basically can control the battery and the fuel cell together and how they combine and work. It also includes air handling equipment, so you need to put air into the fuel cell to enable the hydrogen to be recombined with the oxygen to make water, the steam output. You can also see the cooling system, the fan system on the right-hand side, and there's a DC to DC converter as part of the traction power package. This is our lithium-ion battery pack. There's 24 modules. There's two actual batteries. System voltage of about 650 volts. Now, when these two systems combine, we still only have about a third of the power that we currently could get off of the overhead power lines. And that was because we built this as a demonstrator. It wasn't designed to go into conventional passenger service. So we concentrated on understanding the technology and getting the most out of the control system, how these systems will all interact with each other. Refueling process. So on the left of the picture, you can see the back end of a refueling van. We've now actually containerized this in conjunction with fuel cell systems. So this takes our current hydrogen from BOC tanks, BOC tanks, and decants it into the train via using a compressor, and it takes about 10 to 15 minutes. Obviously, the rate of charge can be higher, but it's going to be very much dependent on how much hydrogen you need in these tanks going forwards. So a production vehicle, an in-service vehicle requiring 65 kilograms, it might take longer. The flow rates might be required to be higher, but again, this is about developing the technology and getting the rail industry used to it and being able to demonstrate it. So we've been undertaking some running already at Long Marston, at the Quinton Rail Technology Centre at Long Marston in Warwickshire, where the train is based. We've done lots of running around that test track, but the problem with the test track is that it's quite low speed. We're limited to about 25 miles an hour. And also because of its the loop nature of it, we also have the different rolling resistance. So it's difficult to determine the full performance of the vehicle at this point in time. We have modelled it, we've got some predictions, and I'll explain a bit later on in the presentation about where we are going to go with that. So, on this slide here is all of the companies that were involved in delivering the HydroFLEX train in 9 months from the standing start, and the core project team is shown on the picture on the left. There is no way that we could have done this if there hadn't been a true collaborative effort, a true joint venture, and it doesn't happen very often, I don't think, in terms of schemes like this for the railway. It's very much open collaboration and a real sense of getting things done. And it was a challenge to get the job done in 9 months from scratch, but it was achieved. So I think the BBC website still actually has the presentations that they did from the breakfast show available on the website. So what's next? We went for some InnovateUK funding. They had a funding call called First of a Kind 3, which allowed us to go for mainline testing. I mentioned that the restrictions we had going around Long Marston, limited speed. So we wanted to see what the train would do on the open network. So to do that, we had to go through the full approval process. You can't take a prototype train out onto the UK rail network without going for approval. So there's very much about the safety of the systems on board. It's also, you need to get route approval from Network Rail. There's things like gauging. So gauging means, does your train, is it within a certain envelope, so it's not going to interact or collide with any of the infrastructure, signals, platforms, etc. We also needed to demonstrate how we'd gone through the safety approvals, how we had built in the systems to guarantee the safety and security of the hydrogen system, the battery system, everything that was new onto that train. The vehicle also was subject to an ORR inspection, build inspections, and EMC testing. So we needed to confirm that the electromagnetic signature of the train wasn't going to interfere with any of the systems trackside. That was quite a grueling process, and we have learned an awful lot about it. We are at the point where we're about to go mainline testing, that we've learned so much about how to do vehicle approvals now that it's going to help us when we start to develop this train into an in-service design, which is a future plan. So looking to the future, sorry, I've jumped ahead a little bit. I'll just say about the mainline testing. We're about to do the mainline testing right now. We've got a program of going onto the line, starting around the Cotswolds line. We're hoping to see an ultimate performance of around about 50 miles an hour, but it will enable us to do fuel economy checks and enable us to demonstrate the vehicle to the wider rail industry. Now, if we look in terms of the future fleets, the map that you can see now is a map of the railway network. The red is AC fed, that's 36,000 volts AC, overhead power lines. The green, mainly in the southeast corner, is 750 volt DC routes. All of the grey routes that you can see are routes that potentially act as feeder routes or are routes that haven't been electrified yet. Now, some of these routes, as I previously mentioned, it will be a long time before it will be possible to justify electrifying them. But at the same time, we do want to decarbonise. We do want to get rid of diesel where possible. And there's also the opportunity to, when vehicles come onto the major routes, the electrified routes, if we have bi-mode trains that could switch from, say, hydrogen onto using the electric power source, that would also enable a clean route to delivering a sort of decarbonised UK railway network. So I think that the future for the vehicles is high. It's going to be a long time before we can electrify the vast majority of the routes. So we needed an alternative. And hydrogen is a potential alternative to diesel. It's also a potential alternative to just doing battery trains. It has some significant advantages. So that's the end of the presentation. I'd like to open up to any questions if you have some.
Hi there, Kevin. Thank you for that. So we have several questions. So if I just get started. Okay, so the first one, have you done any comparisons of the capital and running costs of this type of system and using larger battery packs charged at depots and turnaround?
Yeah. So yes, we have. I think that we need to further refine it because we needed to do the mainline testing to get the higher speeds to understand what the fuel economy looks like, just to finalise our models. We think that it is a better bet than batteries, less cost. At the moment, I think one of the issues we have is the generation of fuel. We're using bottles from BOC, which is an expensive way to get hydrogen. When the rail industry starts to use hydrogen, if it starts to generate it itself, using the sustainable route, we think that the fuel costs will be considerably lower than today, to the point where it will be as competitive, if not slightly less so, than diesel. I would say about the equipment costs, so fuel cells also are quite expensive to buy. They're certainly more expensive than diesel engines at the moment for kilowatts per output. But again, you know, they're relatively small scale manufacture, and when you have an increased take-up of technology, more people enter the market, and we're starting to see the arrival of car manufacturers like Toyota and Hyundai looking at producing fuel cells. I can see the cost of fuel cells will start to drop as well, and I don't think they are as intensive in material use as some of the more exotic batteries. So I think in time, I think the cost will start to reduce considerably.
Thank you. And so for a service train, then, you know, to be able to refuel, we'll need to have higher flow rates, but that means higher temperatures. So do you have any proposals on how to manage this?
Yeah, so we have not had any temperature problems with the flow rates we've been using, but there are ways and means of getting around the problem. We've only seen sort of a couple of degrees Celsius increase in temperature during our testing, and the flow rates can be controlled. You can get quite hot temperatures before it becomes a concern. So we don't think it would be an issue, to be fair. We think it will be okay within the time it takes to refuel trains currently.
Thank you. So the next question is about the maintenance requirements. So has an assessment been done on how expensive or intensive the maintenance would be, and do you have an expected service life?
So expected service lives are increasing all the time. We'd say they're on a par with the diesel engines at the moment, looking at the data, and in conjunction with talking to the fuel cell supplier Ballard. They're confident of the life of the fuel cell. There is regular maintenance to be done. There's lots of filters and things to be changed. The tanks and systems themselves are very robust, and we don't see there being any more of a maintenance liability than there is currently on trains. With their sort of the inspection routes that they have currently would be enough to cover the maintenance requirements of the hydrogen system.
Okay, so I have a question here. It's a bit more of a generic question, but from the work that's happened so far in the project, I mean, what are your main challenges to overcome for the next stage?
For the next stage, so well, mainline testing we're just about to do. I think to start off with, the biggest challenge we had was understanding how to do the vehicle approval process. It is complex. It has taken us some time to do, but that I think has been going forwards. Next time when we do a proper in-service vehicle design and not a demonstrator design, we will understand exactly how to do it now. So I think we will be better prepared. We've got to get the industry interested in looking at the technology and demonstrating it where possible to them. I think that there will always be not a reluctance to change, but it's a very competitive market in terms of the costs that our industry faces, and the ability to implement new technology is a challenge in that respect. But if we start to say decarbonisation is the way forwards, and you get the impression now that the world's finally coming around to that realisation, then I think we've got to start to say, well, we've got to do something different. We can't carry on the way we are.
And just on that topic of, decarbonisation and the potential solutions for all of the transport industries, has the HydroFLEX team been teaming up with the other industries like aerospace? And will the results be published in a white paper so it's widely communicated within the industry?
Yeah, so there is some work going on with different industries. So we have been liaising with some bus operators. We've also been in contact with the car manufacturer that are developing a product at the moment. I think that the aviation one we haven't engaged with at all, as far as I'm aware, but that will come now. The recent announcement, for example, the Airbus was looking at the blended wing hydrogen-powered vehicle was really interesting. People like JVC are also considering things like hydrogen-powered diggers and plant equipment. There's lots of applications where this technology could offer a decarbonisation route. And the government is at the point where I think it's starting to decide on strategies and the way forward. It will be interesting to see how it goes, and we hope to be a part of that.
Great. So I have a couple of questions around kind of regaining some of the energy back. So there's a question here about regenerative braking. And also about all the excess heat. Is there a way in which we can recover that?
Yeah, okay. So in terms of regen braking, our current HydroFLEX train doesn't have regen braking. And that was partly because the vehicle that we have doesn't have that facility. However, there are other train types that have the regen braking on them, and it would be a missed opportunity not to use it. So there's no reason why we shouldn't be using regen and put it into batteries. So I'd agree with that. That should be a way forwards. And for if you just remind me of the other point.
Oh, it was the heat.
And the heat. So the heat is a bit of a problem, in so much as I mentioned that the delta of the fuel cell is much lower to ambient. So that the fuel cell's heat is only probably about 60 degrees C. So if you're running on a nice hot summer's day, you've only got 30 degrees to play with. In winter time, I guess there may be an opportunity to use it to power the train's internal heating system. But yeah, I must admit that's one part of the research that we haven't really tackled yet.
Okay. So from the German trial that you mentioned at the beginning of your presentation, what's the key learning? What are the key lessons that have been learned from that?
So there's been it's actually, to be fair to them, it's actually an in-service train. It's on a very specific route, and they've been running it for probably 18 months or more, actually, if not a bit longer. So some of our team have seen the train. We think that, I guess we haven't had that much engagement directly with them. And so, although Alstom are announcing, they have announced a UK train, a UK version of IMechE. I'm not sure where they are with the build of it yet, but Alstom have developed a train called Breeze, which is specific to the UK network. The German gauging requirements are less severe than the UK one. So when the Victorians built the UK rail network, they didn't think about W12 containers, nor did they think about things like double-decker coaches, that kind of thing. So we're a little bit constrained, and so it makes the German approach, the iLint approach, not applicable for the UK. So Alstom's UK approach for their train called Breeze will have to have to be reconfigured a little bit to fit in with the gauging, local gauging.
So there is a question about the Alstom Eversholt execution. So apparently there was a webinar earlier this week by them for the UK, and it is believed that they are 4 years away from a fleet operation.
Yes.
Where do you think the HydroFLEX is in comparison?
I'd like to think that we could have a production design ready to go within 3 years, 3.5 years. I would like to think that we could do it for that. Well, I think perhaps the key difference might be there's two opportunities really for the rail industry. The first opportunity is to build new trains that are dedicated designs for hydrogen power. And the second option is to consider all of the trains that we have in the UK that are maybe halfway through their fleet life. They might be at a point where they will be considered for new engines or some upgrades, and whether or not we could adapt those trains to run on hydrogen. And that's kind of the approach we've taken with HydroFLEX. So maybe the dates are dependent really on the sort of the routes and the duty cycles that we need to do, and how hungry the industry becomes to want to adopt this new technology. So I think the timeline's really depending upon the opportunity to undertake to equip a fleet of trains, rather than perhaps the technology required to do it.
Okay. So just a question about the internal combustion engines. So the discussion was around, using hydrogen as a fuel instead of diesel. But sorry, what about? Let me just read the question to you. What about using an internal combustion engine that uses hydrogen as fuel instead of diesel? And has this been considered? So the question, they mentioned that they suppose that the cost of a hydrogen internal combustion engine is lower than a fuel cell.
Yes. So there have been some projects that have used that approach. I believe BMW had some trial cars that used that very approach. I was under the impression that there were some issues around doing that originally, because BMW didn't continue with that line of development, and Toyota have gone for the fuel cell route. And BMW recently signed some agreement, I think it's with Ford, but I can't be sure, about undertaking fuel cell research. So yes, it is feasible and it has been demonstrated. We at the University of Birmingham haven't undertaken that kind of research ourselves, so I'm kind of probably not best placed to comment on it. But yeah, it is possible, has been done, but I've not seen much recent news about it, whether it's actually turning into a thing or not. But technology changes all the time. There's no reason why it couldn't be done. I'd imagine that the issues might be around the control of the hydrogen into the engine, the mix. Certainly the current fuel systems for a diesel injector using a liquid would have to be completely rethought. So whether it be possible to maybe start up on diesel and then run on hydrogen, and how you take how you then take the diesel system out of use, whilst maintaining the timing. Yeah, there's those sort of issues. You've got to think about the injector lubrication, the pump lubrication. Yeah, so there's some issues, but yeah, I'm sure these things can be developed.
Okay. So the proposed change from franchising to concessions for rail services, is that likely to affect the supply chain interest?
Yeah, I think so. I think once we can start demonstrating this technology and there becomes a demand, the supply chain will follow. Really, there are already some very good suppliers in the UK that have helped support the project. Whilst we had to buy the fuel cell from Ballard, which is a Canadian company, but things like the fuel tanks and things come from the UK. The batteries came from the UK. The control systems developed in the UK. So, and then there's more manufacturers getting interested in fuel cells. So I do think that the supply chain would benefit from this technology.
Okay. So this question, what are the obstacles for an electric train to generate its own hydrogen powered from the OLE, e.g. a different form of bimode?
Yeah. So to power up an electrolyzer, yes, I don't think it's been thought about. Again, it would be technically feasible to do so. You would have to package it onto the train. So making the hydrogen would be one thing, but you'd still have to then store it on the train as well and still have the fuel cell to power it. So you'd start to impact possibly on passenger space. But yes, technically it's feasible. So you could generate the hydrogen off an electrolyzer. I don't know how well it would package onto a train though. We haven't considered that, I have to say.
Okay, so the demonstrator shows that the equipment's in the saloon area. Do you envisage a production system having the equipment under frame mounted, or will it require a power car with the equipment above the solbar?
So we believe that we can package underneath the vehicle. So the Class 319 that we've been using, there's not much equipment under each driving cab, so we feel that we could package it under.
Okay, and question about the control system to manage, how does the control system manage the power supply and functioning the system?
So it has a number of inputs. There's the driver input for demand, for performance. There's battery state of charge. There's the fuel system. The fuel cell can be configured as to charge the batteries to provide traction power. So it's dependent on a bit like a system map, really. So you're trying to blend the batteries and the fuel cell to provide the performance required by the driver, and that's part of the system that we are doing ongoing development with. So we started off controlling it all off a laptop, and we've started to improve the control system more and more to make it more autonomous. So it's an act of mixing supply and demand, as always.
So are there plans to integrate H2 generation and storage into local microgrid developments?
Yeah, so there is that opportunity. We've done a piece of work for RSSB looking at the infrastructure required to support hydrogen trains, and we've looked at that. So if anybody's interested on that report is actually available off the RSSB website, and it considers how we could support a fleet of trains with a refueling solution.
Okay. And at the moment, what is the TRL level associated for the project, for the HydroFLEX?
Probably about 4 or 5, I guess. Yeah. I mean, we're at the point where we've able to say yes, we've demonstrated it. It works. We know all of the things we need to do, but we need to now consider how we implement that on an in-service design.
Okay, so I think we have time just for one more question.
Mm-hmm.
So the question is about the weight of the trains that you've tested so far. So
Yeah.
the question is about, how much does the system weigh? And mentions that the class 319 at the moment is pretty heavy.
Yeah.
Presumably a production version would be more likely to be designed to fit on the underframe of the DTS vehicles,
Yeah.
as per the diesel engine and batteries on the other flex units.
Yes, that's correct. So it will be more distributed. So you're quite correct. So the way the train is configured at the moment, we have put our equipment into the same car with all of the transformers and equipment that controls the overhead power line or the 750 DC shoes. So all of the choppers and the DC to DC interfaces, AC interfaces, all on that train, on that coach. So we have added, the weight we added to that coach was probably akin to half full of passengers. But if we were to distribute the hydrogen systems, battery systems to each driving car, then the system would be much more balanced, and we would still be able to carry a full complement of passengers on every single coach.
Perfect. Thank you very much for your time, Kevin. And there was a lot of questions being thrown your way, so thank you. Thank you for your time.
Thank you.
And I just like to say thank you to everybody that joined the session today. Please just keep a lookout for further events that the panels will be running. If anybody is interested in joining the Young Members panel or any of the other IMechE panels on a voluntary basis, then just please get in touch. So yeah, I just would like to leave and say thank you and have a good day.
Thank you.